Hello and welcome to this online course entitled Make Your Research Reproducible. My name is Özgün Ünver and I'm a data steward at Vrije Universiteit Brussel, also known as VUB. This video series are meant to complement the PDF document we have uploaded on Zenodo to guide you in your reproducibility journey. You will be able to find the link to this document in the description section of this video. A quick note about this series. This course starts with teaching you the basics of reproducibility in the context of responsible conduct of research, open science, and research data management. Subsequently, it goes into detail as to how reproducibility can be achieved in both qualitative and quantitative research. And finally, it provides you with tools, resources, and actionable recommendations. Once you complete this training, you will know how reproducibility might look like for your research and which strategies and tools you can use to make your research reproducible. Let's start with the introduction to reproducibility. Research is reproducible when others can obviously reproduce the results of a scientific study given only the original data, the code, or documentation. And reproducibility is vital for the credibility of scientific research. It allows other researchers to verify findings, build upon them, and apply them in practical contexts. When a study is not reproducible, it raises questions about the credibility of scientific findings and can even erode the trust in researchers publishing these findings. Therefore, ensuring reproducibility is a critical goal in the research community, involving transparent and detailed reporting of methodologies, open sharing of data and code, and rigorous peer review processes. And unsurprisingly, this concept, reproducibility, is a cornerstone of scientific integrity and responsible research practices, ensuring that research findings are reliable and can be trusted. There are many ways and levels to make your research reproducible, depending on whether you can share your original data, code, and/or detailed and complete documentation. And we call this the continuum of reproducibility. We speak of a continuum as reproducibility is not a binary state, reproducible or not, but rather a spectrum where different levels of reproducibility and validation can be achieved. And each stage of this continuum reflects a higher degree of transparency, detail, and accessibility in research reporting. Moving research towards the more reproducible end of the spectrum is a goal for many scientific fields, as it enhances the reliability and trustworthiness of scientific findings. And here on screen, you can see the general stages along this continuum. The first stage is non-reproducible research, and at the lowest end of the spectrum, research cannot be reproduced at all. This may be due to missing data, lack of detailed methodology, or other critical gaps that prevent others from repeating the study. Second stage, partially reproducible. Here, some aspects of the research can be reproduced, but not entirely. And this might be due to partial availability of data or methods, or because only some results can be reproduced with the provided information. The third stage is mostly reproducible, and at this stage, most of the research can be reproduced by independent parties, but there might still be some minor elements that are difficult to reproduce. This could be due to slightly ambiguous methodology descriptions or minor data issues such as outliers being removed but not described. The fourth stage, fully reproducible, which represents the ideal situation where all aspects of the research, including data, methodology, and analysis, are available and sufficiently detailed so that independent researchers can fully reproduce the study and its results. And beyond this stage, we have open and collaborative research, and this goes beyond mere reproducibility. And this stage represents an approach where research is conducted in an open and collaborative manner from the start. And it involves sharing data, methods, and findings in real time and through open access platforms and facilitating continuous verification and collaboration. In other words, such research is reproducible by design. Now, think of a scientific knowledge as a house. There are endless ways of building a house and endless combinations of materials to use, and endless ways of designing and decorating it. However, no matter how beautiful a house looks from the outside, if the foundation is not robust and reliable, the house will never be a safe shelter. And in science, that foundation is reproducibility. Scientific knowledge relies on building upon each other's work, and reproducibility is essential to build reliable scientific knowledge and foster trust in research outcomes. Reproducibility of the research results adds to scientists' credibility within their research community. Research that is not reproducible is essentially a waste of resources, be it time, money, or expertise. Moreover, this waste of resources grows as other researchers build their work upon the results of an unreproducible research. Even worse is the potential for unreliable research outcomes having detrimental effect on humans and other living beings, as well as the environment. For example, in the field of medicine, unreliable research can lead to incorrect treatments, unnecessary procedures, or missed opportunities for effective care. For instance, a drug that might be considered effective based on flawed studies only to cause harm or provide no real benefit to patients. Conversely, effective treatment might be overlooked due to unreliable negative results. In environmental science, as another example, unreliable research can lead to inadequate and misdirected regulations. This can have direct consequences on human health and safety, such as failing to recognize or appropriately address pollutants or environmental hazards. When high-profile research is later disproven or retracted, it can erode public trust in science and experts. This skepticism can lead to resistance to important health measures like vaccines or climate change initiatives and contribute to the spread of misinformation. And it is difficult to talk about scientific reproducibility without also referring to the reproducibility crisis, which led to the increased awareness on this topic. The reproducibility crisis in science refers to a growing concern over the inability to reproduce the results of numerous scientific studies. This crisis originates from the observation that a significant number of scientific studies in multiple disciplines, even those published in reputable journals, are difficult or impossible to replicate or reproduce by independent researchers. For more information on the reproducibility crisis, you can see the article by Baker from 2016. Now, when it comes to reproducibility, we often come across various terms that talk about the same, similar, or interrelated concepts. And this slide is intended to give you an overview of these concepts so that you can understand what is meant when you see one of them. One of the distinctions you might come across is the one between methods, results, and inferential reproducibility proposed by Goodman and colleagues in 2016, which is defined as follows. The method's reproducibility is the ability for a different team to obtain the same results by using same data and same methods, tools, and processes. Results reproducibility is the ability for a different team to obtain the same results by using different data, but the same experimental methods, tools, and procedures. And thirdly, inferential reproducibility is the ability for a different team to draw the same results by using different data and different methods, tools, and processes. This one is especially interesting as not everyone would draw the same conclusions from the same results. The second classification you see on screen is from the Association for Computing Machinery, which has introduced another widely used distinction between the so-called repeatability, replicability, and reproducibility, and defined these three terms as obtaining the same results in the following scenarios. Repeatability, same team, same experimental setup, same data, same measurement procedure, same measuring system under the same operating conditions in the same location on multiple trials. So for computational experiments, for instance, this means that a researcher can reliably repeat their own computation. Reproducibility, according to this classification, means that different teams can come to the same results using the same experimental setup, same data, same measurement procedure, same measuring system under the same operating conditions in the same or a different location on multiple trials. Again, for computational experiments, this means that an independent group can obtain the exact same result using the author's own artifacts. And the third category, replicability, refers to a different team using a different setup, different data, different measuring system in different location on multiple trials, producing the same results. For computational experiments, it means that an independent group can obtain the same results using artifacts which they develop completely independently. The third classification is from the Turing Way from 2022, which contributes to the discussion by differentiating between reproducibility, replicability, robustness, and generalizability, with slightly different definitions than what was proposed before. And according to this classification, reproducibility happens when the same analysis steps performed on the same data set consistently produces the same answer. Replicability happens when the same analysis performed on different data sets produces qualitatively similar answers. Robustness is the case when the same data set is subjected to different analysis workflows to answer the same research question, for instance, by using another statistical software, and reach a qualitatively similar or identical answers. In other words, results are robust if they are not dependent on the specificities of a programming language or an analysis workflow. And finally, generalizability is the combination of replicability and robustness, where the results are independent of a particular data set or a particular analysis method, tool, or software. So many research fields aim for generalizability, which is theoretically the greatest form of reproducibility, as we have seen in the previous slide. In other words, the results obtained in one study should also be found by other researchers when analyzing other but similar data and using different methods. And achieving this level is also the hardest, as it is very demanding of scientific research and also the researchers doing the research. At the other end of the spectrum, we have repeatability as the easiest and least demanding form of reproducibility, because it is the minimum that is expected, that the study results are exactly the same when the same team processes the same data using the same methods. Note that the confusion around the definitions of these terms is still ongoing. And since we are far from a consensus regarding the definition of reproducibility and other related terms, such as repeatability, generalizability, replicability, the easiest way to cover all these various definitions is to simply consider reproducibility as a continuum. In order to avoid any confusion, we encourage you to use the term reproducibility and define shortly what you mean by it every time you use it. For instance, whether you speak of the same or different scientists, data, and methods.